A function itself has a relative maximum at x is equal to c if the f of c is greater than or equal to f of x for any x in some interval ab. So here we have an interval ab, we have some value c somewhere in between that there, and this value, the y value for this value c, should be greater than any x within the interval ab on either side of it. And also a function will have a relative minimum at x equals c if f of c is less than or equal to f of x, which means for the value of the f of c, for the value c, for any x value in that small interval a b, this f of c is going to be less than any value for x in that interval. And here we can go ahead and use the first derivative test to go ahead and find out if f of x has any relative max or minimum points. And what we first want to do with the first derivative test is we want to find the critical numbers of f of x, and then we want to go ahead and test these critical numbers on the number line. And so if f of x has a relative max, that means for our value c here on either side of c, our derivative will be positive on the left-hand side and negative on the right-hand side, which means our tangent line is going to be positive on the left, negative on the right, and that value c is the maximum point at the top. If f of x has a relative minimum, that means our derivative values, our directions switch. So on the left side of our value c, we get negative values, and on the right-hand side of c, we have positive values, which means our tangent line on the left-hand side is going to have a negative slope. Our tangent line on the right-hand side is going to be positive, and therefore we have a relative min at c at the bottom. If we have no extrema at all, that means on either side of c, the derivative values on either side of c are both positive or both negative. And here's kind of a visual value of that, where we have this graph that goes ahead, comes up, it's a pseudo-cubic, comes up over at c, it kind of flatlines, it has a horizontal line, and then again goes up. So it never truly changes directions at that value c. All right, so let's just go ahead and look at some examples here. So here we want to find the relative extrema of this function. F of x is equal to x squared minus 10x plus 33. And the first thing we want to do is find our critical numbers. So when we go ahead and take the derivative, we end up with 2x minus 10. And this is a polynomial, it's a line actually that's always defined. When we go ahead and set this value equal to 0, we have a critical number at x is equal to 5. All right. So when we go ahead and test that on the number line, and we go ahead and test 5, we find out when we go ahead and plug 5 into our value to the left of 5 into our derivative, let's say 4, we get a negative value. When we go ahead and plug in the number 6 on the right-hand side of 5, we end up with a positive value. So therefore, we have a relative min at x is equal to 5. And we can go ahead and actually find the y value at 5 when we go ahead and plug it into the original function. So when we go ahead and plug in 5 back into our original function, we end up with the value of 8. And so our relative min is the value, the ordered pair 5, 8. Or you could say it's 8 at x is equal to 5. Usually it's better to go ahead and put it as an ordered pair. Let's go ahead and look at another example. So here we have a cubic that we want to go ahead and find our relative extrema. So we have x cubed plus 6x squared plus 9x minus 8. When we go ahead and take the derivative, we end up with 3x squared plus 12x plus 9. And we're going to go ahead, set that derivative to equal to 0. We're going to go ahead and factor out a GCF of 3 to make our life just a little bit easier. And this is a nice little quadratic function that does factor into x plus 3, x plus 1. And setting that equal to 0, we have x values, critical numbers of x is equal to negative 3, or x is equal to negative 1. Let's go ahead and look at that on a number line. So we go ahead, we have negative 3 and negative 1. So we need to find 3 values because we have 2 critical numbers. And so we're going to go ahead, if we go ahead and plug in negative 4 into our derivative, we end up with a positive value. So therefore, we have a positive slope going on. In between the two numbers, -3, -1, -2 is perfect. Let's try that. When we go ahead and put that in there, we end up with a negative value, which means now our tangent line has a negative slope. And now we need to go on the other side of -1, 0. Absolutely, we're going to use that. And when I plug in 0, I end up with a positive value, which again means there's a change of direction. And now my tangent line has a positive slope. So here, where my lines go up to the left and down to the right, that's our maximum. And where it's down to the right, left and up to the right, we end up with a minimum. So our maximum relative max is at -3. And we got to plug that -3 into our function, f of x, we end up with -8. And then our relative min, we're going to go ahead and plug in our -1 into our original function f of x, and we end up with -12. Right, so now let's go ahead and look at number 3. We want to find any relative extrema for f of x is equal to x minus 1 over x. And it's important to note here that we have a vertical asymptote at x is equal to 0 because of the x in the denominator right here. If we go ahead and rewrite our function, we end up with x minus x to the -1 power. And then when we go ahead and take the derivative of that, the derivative of x is just 1. The derivative of -x minus x to the -1 is a positive now x to the -2. And so our actual derivative can be rewritten as 1 plus 1 over x squared. Now this function here still not defined at x equals 0. But it's not a critical number because our original function also could not be 0. So even though it's not defined at x is equal to 0, the original function wasn't either, so it's not a critical number. Okay, when we go ahead and take our derivative and set it equal to 0, that can't happen because we can't have a 0. It won't happen because we can't have a 0 in the denominator there. And so we have no critical numbers. 1 and 1 over x squared are always going to be positive. Okay, x squared, whatever you plug into x squared, is always going to come out positive, but this values are never going to be equal to 0. Okay, because of the plus in between. Since there are no critical numbers, we have no extrema for this particular function. All right, so without graphing this, you could tell that there's no extrema for this function. But remember, we have that 1 over x going on. And we saw an example of that in 5.1 of the type of graph it looks like. So it kind of makes sense to us. Let's go ahead and look at number 4. And I want to find any relative extrema for this rational expression, x squared minus 2x plus 1 over x minus 3. Now we have to remember there is a vertical asymptote at x is equal to 3, and so because there's a vertical asymptote, we will have to include it when we go ahead and do the test here. And now this is a rational expression, so we have to go ahead and use the quotient rule. And using the quotient rule, of course, we go ahead and take the derivative of the first piece times the denominator minus the derivative of the denominator times our numerator, our top piece, over our denominator squared. Okay. When we go ahead and FOIL that, we end up with 2x squared minus 6x minus 2x plus 6. Remember, the minus here carries over into everything else here, just changes the signs. So we have negative x squared plus 2x minus 1 over our denominator squared. Cleaning that up, we have x squared minus 6x plus 5 over our denominator squared. We're going to set that equal to 0. Okay. Now when we multiply both sides by the denominator multiplied by 0 is still 0. So we're really just dealing with the numerator, which factors really nicely into x minus 5 and x minus 1. And so our critical numbers here are x is equal to 5 and x is equal to 1. But remember, we had our vertical asymptote at 3. So as we're testing, we have to also include values around 3, we have to test all of those things. So our number line here, we have 3 different values we're testing. We have our 2 critical values as well as our vertical asymptote. So we have a whole bunch of different intervals here to check. Checking to the left side of 1, checking with 0, plugging 0 into our derivative of our function. We go ahead and we end up with a positive value. Right. Going ahead and plugging in 2 in between 1 and 3, we end up with a negative value. If we go ahead and plug in 4 into the derivative, that's the number between 3 and 5 I chose, I end up with a negative value. So notice on either side of our vertical asymptote, it's both negative. And then on the right side of 5, we go ahead and plug in the number 6 and we get a positive value. Okay. And so on to the left of 1, we have a positive slope. On the left of 1, we have a negative slope. On either side of our vertical asymptote, we have negative slopes. And then on the right-hand side of 5, we have a positive slope. So here at 1, our critical value, we have a maximum. At 3, our vertical asymptote, nothing is going on. It's not changing directions. And at 5, we actually have a minimum. And so we have a relative max at 1. We plug that into our original function and we get 0. And then we go ahead and plug 5, which is our minimum value, and get our y value of 8. Okay. Last one here we're going to look at, number 5 here. Here we have f of x is equal to 2x plus ln of x. So here we have a natural log of x. All right. And if we go ahead and take the derivative of that, we end up with 2. Now remember, the natural log of x, the derivative of natural log of x is 1 over x. So therefore, our derivative is not defined at x is equal to 0. But remember that our original function is not defined at x equals 0 because of the ln. Okay, so because of the natural log. So when we go ahead and plug those values in, we end up with 2 plus 1 over x, set it equal to 0. Here they went ahead and subtracted the 1 over x to the other side. Whatever value you wanted to move first would be totally up to you. Going ahead, multiplying both sides by x, I end up with 2x is equal to negative 1. All right, and then x is going to be equal to negative 1/2 when we go ahead and do that. But our domain of our function, our original function, our 2 plus ln of x, we have only, our domain has to be positive numbers because of the ln. So our domain is 0 to positive infinity, because the ln is only defined when x is positive. So therefore, this function has no extrema at all because the critical value here falls outside of the domain of the function.